Hello and welcome to revision day 2 for Unit 1, Level 3, Applied Science, and today we're looking at bonding. There is a very abbreviated list here from the specification about the 3 different types of bonding. To find out in more detail, please look at the specification that's available on Teams. In general, what we need to be able to do for each type of bonding is give a definition that is suitable for Level 3. We need to be able to draw the type of bonding. We need to be able to explain the properties of each type of bond, and we need to be able to say what affects the strength of each type of bond. The first type of bond we're looking at today is ionic. The definition here is that oppositely charged ions are held together by electrostatic attraction to form a giant structure or a giant lattice or a crystal lattice. Any of those would do for the third mark. Please do not say that an ionic bond is between a metal and a non-metal. That is absolutely true, and it's a fantastic way of identifying if something is ionically bonded, looking at whether you've got a metal and a non-metal. However, it will not get you marks as a definition in the exam. If you are stuck in the exam for a definition for any of the types of bond, all of them include electrostatic attraction. So always start with that as your definition, and then you can explain what it's between. If you forget, at least put down electrostatic attraction and get 1 mark on that question. If you remember by the end of the paper, you can always come back and add it in. In terms of the diagrams, you may be asked to draw the lattice structure shown on this slide, where you've got alternating positive and negative ions. It acts in all directions, the ionic bond. It's not just acting in one direction like the covalent bond is. So do be aware that that's a 3-dimensional attraction. And please also do not get this diagram confused with a metallic bond. Read the question carefully and make sure you're being asked to draw an ionic bond and not a metallic bond. The properties of ionic compounds is that they conduct electricity, but only when they're liquid. That means when they are molten or dissolved. The reason for this is that the ions have to be free to move to carry the electrical charge or the current. In a solid, the ions are fixed and therefore they can't carry that charge. High melting and boiling point count as 2 separate properties, and that is due to the fact that the electrostatic attraction between the oppositely charged ions is very, very big. Therefore, that means they're strong bonds and they're going to require lots of energy to break them. The properties there are physical. They are showing you how the ionic compounds interact with things around them, rather than chemical properties. Chemical properties are reactions that compound can have. The words in blue are there to try and highlight what the marks on a mark scheme will be for, so it's worth going over these and getting used to making sure your answers cover the parts that are in blue, because that is where you're picking up your marks. You have to be able to draw a dot and cross diagram for ionic bonds, so we are going to practice here with magnesium oxide. Magnesium, if you look it up on the periodic table, has 12 protons and therefore 12 electrons, and due to the fact it's in group 2, it's going to have 2 electrons in its outer shell. Oxygen has got 8 protons and therefore 8 electrons, and it's in group 6, so it's going to have 6 electrons on its outer shell. Hopefully you can see oxygen's got 2 gaps where it's wanting some more electrons, and magnesium handily has 2. So those electrons are going to move over to the oxygen to give the oxygen a full outer shell. However, if you leave the magnesium as it's shown now on the screen with no electrons in its outer shell, that looks like magnesium has no electrons at all. And therefore it's really important that you do put on the 10 electrons showing the 8 in the outer shell for the magnesium. So you must show the next shell in for the magnesium with 8 on. You cannot leave that shell blank. That would imply no electrons at all. Now the magnesium has lost 2 electrons and the oxygen has gained 2. So they're both going to have charges. They are now ions rather than atoms. So we're going to put square brackets around those. This shows that the charge is over the entire thing, not just on one part. And as the magnesium lost 2, it's going to have a positive charge because it lost 2 negative electrons. So it's going to be 2 plus. The oxygen gained 2, so it gained 2 negatives, so it's got a 2 minus charge. So now we're showing here a magnesium ion and an oxide ion. You do not need to show the electron configuration as I have done under the brackets. That was just to help us keep track of how many electrons they had. However, if you want to do that in the exam so that you make sure you know how many electrons things have got and that's your rough working, that is absolutely fine. One final note on this diagram is that we cannot refer to this as an oxygen ion. Once it has become an ion, we must refer to it as an oxide ion. Have a go now by pausing the video at drawing the ionic dot and cross diagram for calcium chloride. This is what your answer should have looked like. Calcium is in group 2 and therefore loses 2 electrons. Chlorine is in group 7, so each chlorine can only gain 1 electron. But if calcium's losing 2, we've got 2 electrons up for grabs, so therefore we're going to need to have 2 chlorines so that each chlorine can accept 1 electron. Again, please note that we've had to refer to this now as a chloride ion. We cannot refer to it as a chlorine ion. So when we're forming our negative ions, such as oxygen, chlorine, fluorine, we need to make sure we're changing the ending from to an "ide" ending. So we would have, for example, a fluoride ion or a bromide ion. You will lose marks in the exam if you do not refer to them correctly. The strength of the ionic bond is due to both the charge on the ion and the size of the ion, which we can refer to as the ionic or atomic radius, when we're thinking about the sizes. When a metal becomes an ion, it loses electrons. This therefore means it's got more protons than electrons, and therefore the protons are going to pull the remaining electrons in closer to the nucleus. So by losing electrons, the ion gets smaller, not because the electrons have been lost, but because the overall charge of the nucleus compared to the remaining electrons is bigger. The bigger the charge on a metal ion, the smaller the ion will be. So here, the magnesium 2+ will be smaller than the Na+. If we had aluminium 3+, that would be smaller still. The reason is it has more protons in the nucleus of the aluminium than of the magnesium and of the sodium, and therefore the remaining electrons are pulled in more closely. Therefore, the attraction on an aluminium ion is going to be greater and therefore have a stronger ionic bond than for a magnesium or for a sodium. This will impact the melting and boiling point, so the higher the charge and the smaller the radius, the higher the melting and boiling point will be. The opposite is true for non-metal ions, as they gain electrons when they form an ion. So non-metals are gaining an electron. This weakens the attraction to the nucleus because they now have more electrons than protons. This means their ionic radius increases. Here you can see a fluoride ion and a chloride ion. Chloride ions have a whole extra electron shell, so they are much larger than a fluoride ion. This means they have a bigger ionic radius and therefore a weaker electrostatic attraction, and therefore we would expect the melting and boiling point of a chloride compound compared to a fluoride compound to be lower because the attraction is weaker. Covalent bonds have a definition different from what you learned at GCSE. At GCSE, a shared pair of electrons was enough to say, but now we need to say what the electrostatic attraction is between. So the electrostatic attraction is between a shared pair of electrons and the positive nuclei. They may be shown to you in multiple different ways. As you can see in diagram A, we can use just a line to represent the shared pair of electrons. 2 lines would represent a double bond, 3 lines would represent a triple bond. In diagram B, you can see overlapping circles with a dot and a cross in, showing the shared pair between the carbon and the hydrogens. We do not have to have the circles, however, anymore at level 3, and you should be capable of drawing diagrams like diagram B for not just methane, which is what's shown there, but for also carbon dioxide, ammonia, ammonium, oxygen, hydrogen, water, and other simple covalent molecules. If you're not confident in drawing those, please look back through your Unit 1 booklet where you've got worked examples and practice drawing those out. Diagram C shows the 3-dimensional structure. The hashed line to the H on the left-hand side of diagram C, the dashes show that that hydrogen is going behind the screen or behind the paper if it's an exam paper. The wedge shape for the middle hydrogen at the bottom shows that it's coming out of the screen or out of the paper. And the attraction in a covalent bond is only in one direction. It's between the two nuclei. It is not a three-dimensional attraction. You need to be able to explain how bond length and strength changes as we go from a single to a double to a triple bond. In a single bond, there is only 2 electrons, the shared pair. And in a double bond, we therefore move to 4 because we have 2 shared pairs. In a triple bond, we have 6 because we have 3 shared pairs. The more electrons we have, the greater the nuclei either side of it are going to be attracted. And this will therefore decrease the bond length. So the more electrons we have, the shorter the bond is getting. However, the bond is getting stronger. So the bond will get shorter because the attraction is greater, but it's also getting stronger because of the more attraction. So it will require more energy to break. Therefore, the triple bond will have a higher melting and boiling point than a double bond, and the double bond will have a higher melting and boiling point than the single bond. But you must link this back to the number of electrons in between the nuclei. You must know a definition for a dative, sometimes called a coordinate bond, and in this, both electrons in the shared pair come from the same atom. You are allowed to draw a diagram to show this in the exam. However, you may be asked to write it in words instead, and you'd need to therefore say the shared pair come from the same atom or element. The diagrams below show the drawing of how you can show both electrons going from the nitrogen to a hydrogen ion in the ammonium ion, which would be NH4+. Giant covalent compounds such as diamond, silicon dioxide and graphite are generally tetrahedral in structure, and therefore they're forming 4 single bonds. Graphite has a slightly different structure to that, but you don't need to know it for the Unit 1 exam. If you see something like methane, which is a simple covalent, but shown below, with 4 single bonds, that is tetrahedral structure, and it has a bond angle of 109.5. This is the biggest angle those shared pairs of electrons can be apart from each other. Electrons are negative and therefore they will repel and try and move as far away as possible. You must know the bond angle of 109.5 for any atom that is forming 4 single bonds in Unit 1. Metallic bonding is our last type of bonding, and it's often the easiest. It is the electrostatic attraction between the positive metal ions and the delocalized electrons. You may draw a diagram to support your definition of this, but if you do so, please make sure you label it to explain what your diagram is showing. Do not get it confused with the giant lattice shown for the ionic bond, which had alternating positive and negative ions. However, similar to ionic, the attraction acts in all directions. Properties of metallic bonds are the same as from GCSE, but it's definitely worth a revise. They conduct electricity and heat really well, so they are good conductors. The reason is they have delocalized electrons that are free to carry the electrical charge. They are malleable and ductile. Malleable means you can change the shape when you exert a force, and ductile means they can be pulled into wires. The reason for both of these properties is that the positive metal ions are arranged in layers that can slide. They have high melting points and high boiling points. This is due to having strong electrostatic attraction between the positive metal ions and the delocalized electrons, which requires lots of energy to overcome. Again, these are types of physical properties. Chemical properties would be to do with how they have a reaction, for example, with oxygen, or if it's group 1, with water. You might be asked to explain how the bond changes across a period or down a group. Across a period, the metallic bond gets stronger. If you look at the charges, we've gone from +1 to +2 to +3. This means we're going to get stronger electrostatic attraction, and therefore the bond is going to be stronger. So the charge increases across a period, meaning stronger electrostatic attraction and therefore stronger bonds. This would mean a higher melting and boiling point the greater the charge on the metal ion. Down a group, However, the bonding is getting weaker. If you look at these diagrams, you can see that they are getting larger. We are getting more electron shells. However, the charge on each ion is staying the same. So lithium and potassium both have a +1 charge. But in lithium, due to it being smaller, that charge is shared out over a smaller area, meaning that the charge density is greater. So, as the number of electron shells increase, the size of the metal ion increases. This means the charge is spread out over a larger area, or there is a weaker charge density. This means the electrostatic attraction is going to be weaker. This will therefore mean a lower melting and boiling point. So down a group, the melting and boiling